So we'll just do a little bit of set notation here in Venn diagrams, which is something you are familiar with. So usually a set is represented by a circle inside a rectangular universal set, and the idea is that the universal set is somehow the natural place where the elements of the set live. Something like this. So for example, some examples would be if you're considering the set of all males alive being A, U might be the set of all people alive. If you're thinking about maybe the set of students in your class, the universal set might be the set of CIT students. And as we said for numbers, if you're thinking about maybe the set of square numbers, maybe the squares of natural numbers, the universal set could be either natural numbers or the real numbers. Okay. There are some paradoxes coming in if you think about the universal set, but we won't do that. We're going to call it an ambient set, because what you want to do is you don't want the universal set to be the set of all possible things. Like you don't want the set of CIT students in the set of all possible things. The problem you end up with is if you consider a set of all possible things is the universal set itself in itself, and if you do that you get all horrible contradictions and maths basically breaks. So we're going to talk about an ambient set. So ambient is kind of a place where things naturally exist as such. So a set may be described by listing its members. So for example, algebra sets, functions 1, graphs, functions 2 is the set of chapters in this manual. There's probably two things that are worth commenting on. As you said before, you don't have duplication. You don't have functions and functions twice. You'd have to have functions 1 and functions 2 to make them different. And order actually in a set does not matter. Okay. Alternatively, a set may be described by specifying a property which only the members of the set have. Right, so for example, P. So this is the set of, now it says not equal to 1. So so far it's just all objects that are not equal to 1. And this is read such that n is a natural number with no factors other than 1 in itself. So is 2 in this? Yes, because the factors are 2 and 1. So it has no factors other than 1 in itself. The factors are 3 or 3 and 1. Now if you take number 4, that has factors other than 1 and 4 because it's got 2. 2 is a factor. So 4 isn't in this set. 5 is in this set because its factors are 5 and 1. 6 isn't because it's 2 and 3 are factors. 7 is, etc. This is the set of prime numbers. Now if you want to house this read, P is the set of n not equal to 1 such that, that's what this bar means, such that n is a natural number with no factors other than 1 in itself. Okay, sometimes you might just write P is equal to n is a natural number with no factors other than 1 itself, or even P is no, okay, right. So this is just saying that you can write down a set by kind of describing a property that only its elements have. Right, next thing, cardinality. Now cardinality is a kind of a, you might say, why do we come up with this kind of word cardinality? Why don't we just say the size or the number of elements? And the reason that we don't do that is because when the set sizes get infinite, it gets kind of complicated. Like you can, like say the natural numbers, there's infinitely many natural numbers, and there's infinitely many integers, and there's infinitely many fractions, and there's way more fractions than say natural numbers, but you can show in a specific sense that there's actually there's this kind of the same number of them. Things just get complicated, so that's probably why we use the word cardinality. But cardinality just means, certainly for a finite set, is the number of elements it contains, and you denote it like this. Now, one of the things that, you know, we're going to be using notation. We have to do this. You're going to have to, now in my opinion, the way you learn notation is you kind of just do exercises and you get used to it. If you want, it's something like absolute value, which for numbers is like the size of the number. It doesn't say kind of is it plus or minus, just as how big is it in a certain sense. Like minus 100 is big, it's about as big as 100 is the thinking. So this bar means the number of elements in the set X. Okay, so we'll be looking at stuff about that later. A set B is a subset of a set A. Now we write it like this. So these are the notations you're going to have to get familiar with. B is a subset of A if every element of B is a member of A. Now the way to think about this, as far as there's different ways, but for me it's a set that is inside another set. Now it's not an element, but it's like a sub-collection. So I think we even have one up here we can write. So it's a set inside another set. Everything in A is also in U. So A is a subset of U. Okay. So for example, C, people born in Cork, and M, people born in Munster. C is a subset of M. Every person born in Cork is born in Munster. Okay. In terms of Venn diagram, so I'm not going to specify what the U is here. No, I think this is just a Venn diagram for subsets. I'll write a few of them here. So that's the set A and a subset B. Now B is still a set, but every element in B is also in A. So we can write B is a subset of A. Now A is also a subset of U while we're here, and B is also a subset of U. And there's something that we're going to talk about later. B is a subset of A, and A is a subset of U, and that means that B is a subset of U. So this is what's called a transitive relation. Okay. A set can have no members, in which case we call it the empty set. Now you've got two symbols. This thing here, I don't know exactly what this means. Maybe it's like the zero you're thinking of as a Venn diagram kind of job, and the line going through it saying there's nothing in there. Or else you can list all the elements. So remember, how do you list the elements? Say like this, you list all the elements. So start up a list and put nothing in it. Both of these are good. Now what you cannot do, and I know I'm going to see it because I see it every year. So the question is, what about this? So this is kind of a combination of two. This is not the empty set, because this set has the empty set in it. This is a set containing the empty set. So if I write something like the empty set is in the set containing the empty set, so that means that this has elements, the empty set. So this is not how you write the empty set. So if you write this, this is incorrect. You can write this or this, not a combination of them. So examples of the empty set: the set of CIT students that are older than 200 years old, set of whole numbers strictly between 1 and 2. Think about the numbers strictly between 1 and 2 that are whole numbers. There's none of them. Where C is the set of those born in Cork, and W is the set of counties containing the letter C intersection W. That's empty. Now we'll kind of draw this. Okay. Now the universal set here is a bit difficult. So what am I putting in this thing? I've got set of those, that's people, and also I have counties. So I'm going to have to form a universal set. Now I'm going to use a symbol that we'll see later on. So the universal set is the set of people union the set of, I'm going to call it counties. So, well, I can't call it that. So I'm going to call it C dashed. So C dashed is equal to a set of counties of Ireland. Now this union, one of the problems that we're going to see it later on is probably you think about it in terms of and you say, oh, it's all the people and all the counties, but it's not really an and, it's an or. So this is the universal set contains all the things that are in P or in C dash. So it's all the set of things that are either a person or a county in Ireland. So now we haven't even said what intersection is yet, but we'll show it. Okay, so the set of people born in Cork, people, and the set of counties containing the letter W. So we'll throw in Wexford there, for example. People born in Cork, Oh, I don't know. Can't think of any Cork people. Sonia O'Sullivan. Okay, so there's no. So this is the people or the things that are people born in Cork and counties containing the letter W. Of course, there's no person is a county, no county is a person. So the intersection is the things that are in both of these. There's none of them. That's the empty set. Okay. So given a set X, the set of subsets of X is also a set. Now this is where you're getting ideas on top of ideas, which is a little bit difficult, I appreciate. So probably the best way of doing it is just doing an example. So X is a set ABC. I'm going to form a set. Now this is another bit of notation, P of X. So the P stands for power, but really I want you to think of the subsets of X. Set of subsets of X. That's what this is. Okay. That's a set. So we need to get sets, because it's a set of subsets or sets. So we need sets that are subsets of ABC. Okay. So what are subsets of ABC? So let's see what did we say was a subset on the previous page. A set is a subset if every member of B is a member of A. Okay. So let's start off with maybe the easiest subsets. The set containing A. This is a set, and everything in this set is also in this set. The only thing in here is A, it's in there. This is a subset. We might draw a picture in a moment. The set containing B is a subset of this because everything in this is in this. Set containing C, that also works because everything in this set is in this set. Now they're the one element subsets. These are called the singleton sets. We can go a bit further. And what about the two element subsets? So what about A and B? Yeah, that'll work. Now I'm just going to continue over here because I want to draw a picture in a second. Yeah. So do I even want to draw a picture? No, I'm not even going to draw the picture. A and B. What about B and A? Or what about A and A? So we'll do A and A first. You wouldn't have A and A because sets do not have repetition. AA, the set AA is just the set A. Let's write this down here. So you don't include repetition. Now if there are truly different A's, then that's fine. You probably want to write one of them different, maybe A1 and A2. But here where they're just the same thing, this is the same as the set A. Okay? So I don't have the set AA, for example. And what about the set BA? Well, the set BA, well, the other thing about sets is order is not important. So the set containing B and A is the same as the set containing A and B. So I don't include AB and BA. What else we got? A and C. And finally, B and C. Now there's two more subsets. One of them is you take all of them. Now this wouldn't be a proper subset, but it is a subset because everything in this set is also in this set. And there's one more, the empty set, which I'm going to write as, actually for this I'm going to write it like this. Okay, the empty set. Now you might say, how is the empty set a subset? Now that's a little bit tricky, and I think I'm going to talk about it down below. But we get what's called a vacuous statement. It's a statement that, so let's say what a subset is. Everything inside here must be inside here. Now if there's nothing inside here, there's nothing to check, essentially. So it's vacuous, what's called vacuously true. Now you can just always say, oh, it's always a subset. The empty set is always like the empty set is even a subset of itself. But that's more like the set ABC is a subset of ABC. Now there are alternatives just for two bits of writing here. You could have written ABC just as X. That's okay, but not as the set containing X, because that wouldn't be correct. And similar story, you can take the empty set, you could have written it as the empty set like that, but again, not equal to, do not write the set containing the empty set. In general, and in fact always, the cardinality of this, the number of subsets, is 2 to the power of the cardinality of the original set. That's probably a reason why it's called a power set. So if we count the number of elements here, you get 1, 2, 3, 4, 5, 6, 7, 8, which is 2 to the power of how many things, what's the cardinality of x, is 3, 2 to the 3. So now you don't write that p of x is equal to 2 to the 3, that doesn't make sense. The number of elements in p to the x is 2 to the 3. Yeah, okay, now we'll have examples where we'll see what's right down. So what we said in the previous page, particularly the vacuous thing, like you should be a bit confused. Why is the empty set a subset? Here's a different way of explaining it. So one way to think about subsets is as follows, where x and y are sets, a subset of x, subset of y, corresponds to a choice of elements of y. So you can think of a subset as a choice of the elements. So for example, y equal to 1, 2, 3, 4, a subset is formed by answering these questions. Is 1 in x? Is 2 in x? These should all have question marks. Is 3 in x? Is 4 in x? And the answer every time is yes or no. For example, the subset 1, 4 says yes, no, no, yes. So this subset 1, 4 corresponds to choosing 1 and 4 but not 2 and 3. If you choose all of the elements, you have the full subset. So this is the same as this. So if you say yes, 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 then y is a subset of itself. So in that sense, we have that y is always a subset of itself. Like what we had here, ABC is a subset of x. X is a subset of x. Now what if you say, instead of all yeses, say you say no. Is 1 in x? No. 2 in x? No. 3 in x? No. 4 in x? No. No more questions. This is a set containing no elements. It's a choice, a selection of elements from the set x, and you've just you've chosen none of them. And in that sense, you have that the empty set is a subset of y, or you can write the set containing no elements is a subset of y. So a subset corresponds to a choice of elements of y, choosing none as a choice, and therefore the empty set is always a subset. Now the next page, unfortunately, is a waste. Now what's not explained here, what's not explained is why is the subset a subset of itself. And it is, but why? Unfortunately, I can't. You're just going to have to take my word on it. One small thing that's worth saying here is you can have, I've written subset here, and usually that means it doesn't consider equals, but it's not like less than or equals, where it's, the convention is a bit off. So sometimes people write subsets, sometimes people write subset equals. I think to be clear, you want to say if I take the set 1, 2, and the set 1, 2, 3, if you want to really emphasize that it's not equal, you wouldn't use the subset without the equals. You'd actually do something like this. 1, 2 is a subset, so it goes beyond less than rather than less than equals. You'd say not equals. So it's a subset of not equals. Okay. Right, where are we? So when we list all the possible subsets, all the possible choices, if we list them, make a set of them, that's the power set of subsets. Okay, so let's do some examples. So list the elements of the following sets, the set of vowels. So there is going to be time to time just some kind of common knowledge that you'd be expected to know. You can't learn these things, just the hope is that you have this knowledge before you come here. So an example of, what are the vowels would be an example of it. Now if you're listing elements, I want to see the set brackets, the curly brackets. So what have we got? A, E, I, O, U, and I appreciate maybe it should say the set of vowels in the English alphabet, because there's more vowels in other alphabets. Okay, so let's look at this next one. This x is n, so x is a natural number, 1, 2, 3, 4, 5, 6, 7. It's less than, it's great, it's between, this basically means it's 10, between 10 and 20, possibly equal to either. Now we might actually write down what this means. So this means it's greater than 10 and less than 20. So really what does that mean? Well, if it's a natural number, it's 10, 11, 12, 13, up to 20. It's one of those numbers and divisible by 3. Okay, now divisibility by 3 is something we're going to see here and there. Let's just write what it means specifically. What is a definition of divisible by 3? A number is divisible by 3. Now, I don't know why I have the difference here. Yeah, because this could have just said, doesn't need x minus y. So, yeah, okay, so maybe we should just write x divisible by 3 if, and only if, the number divided by 3 is a whole number. Okay, so what are we going to get here? So we're taking natural numbers between 10 and 20, so that's 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and it's divisible by 3. So we could just check each of them. 10 divided by 3 is not a whole number. That's not really badly. That's supposed to say z. 10 divided by 3 is not a whole number. 11 divided by 3 is not a whole number. 12 works. 12 divided by 3 is 4, and that's what it means by divisible. That if you divide, you get a whole number. 13 divided by 3 doesn't work. 14 doesn't work. 15 works. 16 doesn't. 17 doesn't. 18 does. And if we any more, no, because 19 is not divisible by 3, and 20 is not divisible by 3. Okay, so that's that. Right, let's keep going. Now, it's funny here, it goes on about unions and intersections and stuff, but I haven't actually got there yet. So we're going to have to go back to this particular question, because strictly speaking, I haven't spoken about unions and that. Okay, right. Next question. So we have the set containing 3 elements, x, y, z. So let's just write down the number of elements in S is equal to 1, 2, 3, 3. List the elements of P of S, i.e. list all the subsets of S. So all the subsets of x, y, z. So we're going to think of it in terms of a choice. We'll try and do it that way. It's the same as what we did over the previous page. Hence, now hence means using this, or otherwise write down the value of this. Now the or otherwise I can do now, because we know that the number of subsets in the power set, the set of subsets, is 2 to the power of the number of elements in S, and there are 3 elements in there, so that's 2 to the power of 3, 2 multiplied by 2 multiplied by 2, which is just equal to 8. So that's that question done. Or else we can do part 1, and how would you hence? Well, if you listed all the subsets, you could just count them. Right, so what we're going to do here is we're going to maybe see, can we write it in the way, so we got x, y, z, we'll ask it as questions. So is x in a subset? Now subsets we'll call them, let's call them R. It's y in the subset. And is z in the subset? And then we list all the possible answers. Okay, so the first thing we could do, so this is the power set of S, is if we say yes to all 3 questions. Yes, yes, yes. Now that'll be the set containing x, y, z, and I could write the set containing x, y, z, but how about we just write, instead of the set containing x, y, z, we just write S. How about we say yes, no, no? That'll give me x. How about I say no, yes, no? That'll give me this y. How about no, no, yes? That'll give me z. And then I suppose at this point you want to keep going, but you'll remember from here that there's going to be 8 of them. How about yes, yes, no? That'll be x and y. Yes, no, yes is x and z. How about no, yes, yes? That'll be y and z. And finally, how about no, no, no? That would be choosing none of them. That's the empty set. Now I'll check 1, 2, 3, 4, 5, 6, 7, 8. Yeah, that's good. Okay, so what we're going to do next is we're going to talk a bit more about subsets.